So last time we kind of talked about SQP methods for optimization, which are straightforward, right? Like we know how to do QPs now. SQP is basically just Newton's method, but with inequality constraints. You linearize everything, you get a QP, solve the QP, get a step, blah, blah, blah. Repeat until convergence. And then we use that to do direct collocation, which is sort of the other major paradigm, I would say. Like I would say right now, modern kind of robotics applications, aerospace applications, if you're doing nonlinear trajectory optimization, you're probably doing either like a DDP or a direct collocation. Those are the two big ones. And there's pros and cons. So today, we're just going to kind of like do a brief chat about that, like the kind of relative merits of like the pros and cons of those things. So little recap and just kind of summarize the takeaway messages from that stuff. And then we're going to get into some new stuff, which we'll spend the next couple classes on, which is one of my sort of near and dear topics, which is dealing with attitude. What I mean by that is 3D rotations. Also, you know, like SO3, SE3 pose. So this is like something that's super pervasive in robotics and shows up all over the place, right? Like any floating base thing you do, you know, is going to have this. And I'd say a lot of people like are, especially going back like a few years, are super naive about this stuff. And like there's a straightforward set of ideas here for how to do this properly that really work, super practical. And like it's basically, essentially what we're going to do is just enough group theory for you to be dangerous. I'm going to give you like the practical sort of, you know, kind of dummies guide or Cliff's Notes version of group theory, just enough to like handle the stuff you need in robotics applications. And it's like magic. Like it fixes all the bugs. It's super clean. So I'm going to show you how to do that stuff the right way. So that's kind of what we're going to do. We're going to start that today and spend next couple classes on it. And then you'll be able to like, you know, make drones do loops and make humanoids do backflips and all that good stuff, which is obviously what we want. Okay, cool. Any questions about any of that before we jump in? Okay, sweet. So quick recap then. So this whole kind of like trip we've been on for the last several weeks, we did sort of just optimization crash course material. And then we did like all this LQR stuff and kind of just finished up with nonlinear trajectory optimization, right? So this was all what I would call deterministic optimal control. And we, you know, had a bunch of algorithms that we derived and used. And I'm just going to kind of like try to summarize this a little bit. So for kind of linear or local sort of convex-ish stuff, which we spend a lot of time in. And I would say what I mean by local there is works with linearization. So you can get away with linearizing about an equilibrium or a trajectory or something, which is a lot of stuff, to be clear. Okay, so in that scenario, there's sort of a little bit of a decision tree that you know, I think you can kind of think about, and this is all like pretty straightforward. So basically, the first question to ask is, are there constraints? If there are they like critical? Do they matter? Do you need them? If there are not, then you're in LQR land and life is good. We can get closed form solutions. We get nice little linear feedback policies. That's pretty great. And then the next question there, if you're in LQR land, is, are you solving a tracking problem where you like have a trajectory reference or something like that? Or are you solving a stabilization problem? Like you're trying to just keep the thing at an equilibrium point, trying to hover, trying to balance, that kind of thing, right? And if you are in the stabilization kind of situation, that's a time invariant situation, right? You linearize about an equilibrium point, and time invariant LQR, you get a static single gain matrix. So we'll call that TI-LQR. And then if you're in the tracking case where you have some trajectory, typically that's where you're going to linearize along the trajectory, and you're going to get like a K of T or a K sub K, you know, sort of time varying LQR situation. There are some other subtle variations on these things, right? You can have periodic LQR where it's time varying, but it's periodic. Then you get, as you might expect, periodic gain matrices. That can show up in walking, for instance, where periodic gait, right? So there's some other things, but that's like the main stuff. Okay, so then if we're in the situation where we have constraints and they matter, and you want to reason about those, then we're in MPC land. And in that sort of setting, we've got basically so far, are the constraints linear, or can you linearize them effectively? In which case we've got QP stuff, which we know how to do now pretty well. Plug it into OSQP, right? You can fly our drones with this stuff. It's pretty nice. And then the other option we have here for convex constraints that are pretty common in applications and show up are conic constraints. And the kind of common places those show up in robotics are friction cones for feet and grasping and stuff like that. And in aerospace applications, these frequently show up as thrust cones for rocket engines and stuff like that. And then we're in SOCP territory, second order cone program, where we can put the conic constraints in. And those are used a lot on drones, it turns out, where you can model the thrust cone kind of implicitly via like attitude constraints kind of, and they show up in rocket landing problems, and they show up in legged robot problems where you want to reason about the friction cone. Okay, any questions about that? So that's kind of linear convex land. Those are sort of roughly the things. And then now we'll sort of do a similar thing. Yeah.
TVLQR is where IMQR comes.
TVLQR is not necessarily. It's like this is where I have, let's say I've done nonlinear trajectory optimization, could be ILQR, could be DIRCOL, and I get some insane, let's say a backflip or something, some crazy maneuver so let's say it's, drone doing some barrel roll thing, right? So that's highly nonlinear. You probably can't use a single linear system to model that entire thing, but you can linearize about every single point on that trajectory and get an A and B that are time varying along the trajectory. Then you do a Riccati and you'll get time varying K matrices. And then what you can do is you can roll that out with the LQR feedback, and a single linearization, single K won't work, but a time varying set of Ks will basically stabilize a tube around that trajectory. And that works extremely well. So that's kind of the classical combo, actually. For a long time, like the recipe for doing these crazy things was offline, you do nonlinear trajectory optimization. You get a reference trajectory that might do the crazy thing. And then you linearize around that and write down an LQR tracking controller or a convex MPC tracking controller that's time varying. And that basically will stabilize you within some tube around the nominal trajectory. So like circa 10 years ago, that was basically state of the art. And that's what everything like was doing. And now we're starting to see like the RL stuff kind of take over. But that classically, that's the classic playbook.
So then the simple people talk about level randomization. I'm just referring to linearization.
No, that's a bit more subtle. So what they're really doing is like a sort of like random sample-based version of robust control. So what that's, and there are linear analogs of that. There's an entire theory of linear robust control. So what that's really getting at is errors in the model. So in the linear context, that would mean you have an A and a B. You have a linear system model, but there's uncertainty in the A's and the B's. And maybe it's stochastic or maybe it's bounded uncertainties, right? That kind of thing. In the case of bounded uncertainty in A and a B, there's a very well-developed linear theory that was all developed in the 80s, basically, by people like John Doyle, that tells you like, okay, if you can bound those errors, here's like a recipe for coming up with gains for K matrices that are guaranteed to stay stable for any possible instantiation of those A's and B's within these bounds. So that's like classical robust control theory. And then the domain randomization stuff in RL, what you're doing is you're basically taking your model and putting noise all over it and trying to optimize a single feedback policy that'll work over any of those samples, right, of random model perturbation. So it's a sort of sample-based randomized version of the robust control ideas, right? And there's a lot of related ideas, but that's kind of, domain randomization is really a robust control thing, I would say. Okay, any other questions? Cool. All right, so now we're going to do like the nonlinear trajopt story. So if you're trying to do this sort of, there's kind of, again, we've talked about like basically two schools. And if you go through the literature, you'll see a lot of talk about like direct versus indirect methods, blah, 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 shooting versus whatever. We're going to simplify that conversation. There's a lot of confusion around exactly what those terms mean. And practically speaking, the most popular versions of those things are DIRCOL on the direct side and like DDP, ILQR on the indirect side. So we'll just kind of talk about those two. And I'll try to give you like a pro-con kind of story for both of these. So draw a little thing like this. So first off, like There's sort of on the Dirk-Hall side, we'll talk about the dynamics maybe. So with Dirk-Hall, you're only respecting the dynamics are written as constraints, and you can give it an infeasible guess, but you're only really respecting those dynamics at convergence, right? So that's maybe pro. That's a two-edged thing. It's pro and con in some sense, but this one only respects dynamics at convergence, which, whereas the DDP stuff, because we're doing rollouts at every iteration on the nonlinear dynamics, you're always dynamically feasible. So that's one thing to worry about. So yeah, the idea here is we're going to try to get you I'm going to try to lay out the differences of pros and cons, and then kind of which one to choose is very application dependent, I would say. So the other side of this is that the Dirk-Hall stuff, you can use any guess you want, right? So you can guess part of the state. You can write down some random guess that doesn't obey physics. So it's very flexible that way. And that's actually as we saw last time, right? I showed you a swing up thing where we only gave it one component of the state vector and added noise, and that let it converge super quick. So that ability can be really, really helpful. It's also very helpful if you're gluing this together with some other planner, like a sample-based planner that gives you maybe only poses or only center of mass trajectories. You can use that as a guess. Whereas with DDP, you have to you can only guess the controls, and then you have to roll out the dynamics and get whatever you get for the states, which is maybe annoying. And then talking about other constraints, with Dirk-Hall, you can basically handle arbitrary constraints on the states and inputs. You can just write down all the constraints you want, and the solver will kind of do its best. So that's very nice. Well, it doesn't always work. It's
check this constraints.
Yeah, so you can start with some random thing that doesn't obey the constraints, and effectively, another way of thinking about all this stuff is, basically what all these Trajopt methods are doing is you can think about the whole thing as a big projection operator. What it's trying to do is the dynamics constraints are some manifold, right, and trajectory space, and the cost function, if it's a quadratic cost in particular, that's just a distance metric on trajectories, right? So literally you can think if you have a quadratic cost and dynamics constraints, what it's literally doing is you're giving it an initial guess. That's some random trajectory that's off the manifold. And you're asking it to basically give you a dynamically feasible trajectory that's closest to that one under the cost metric, right? So it's very much like a projection, right, that it's doing. So you can think about it as basically a way of projecting your guess onto the manifold of trajectories that obey physics, which said that way, it's extremely analogous to diffusion, right? If anyone's into that stuff, right? These are all really closely related. Okay, so let's see here, right? For DDP, it's hard to handle constraints. In particular, it's very hard to handle state constraints. Input constraints you can kind of do in the backward pass, as we talked about, but hard to handle state constraints. And there's ways to do it, but it's all kind of hacky and a little messy and not great. Let's see. Okay, so then talking about tracking controllers, like we were just talking about, right? Tracking something you've optimized. With DDP, you essentially get that TVLQR tracking controller for free. At convergence of DDP, the K matrices are the LQR tracking controller that you would get anyway. So that's kind of cool and possibly useful. In fact, that is quite useful in applications because a lot of times, if we're doing this online, we can't solve the nonlinear Trajopt problem fast enough. So what we'll do is approximately solve it with DDP, take a couple iterations, and then in between those solves, we'll track that with the LQR tracking gains that come out of this thing. And that lets us run a much, much higher rate, low-level feedback controller that say I can only solve the DDP problem at 10 hertz. I could go run that K matrix with a 500 hertz low-level feedback in between those solves, and that can help a lot. So that's nice. Whereas with Dirk-Hall, you basically have to design that tracking controller separately, which is not such a big deal. But There are some tricks there too. Okay, let's see. There's that. What else are we gonna say here? And then yeah,
When you do that, where you like are burning DDP at a much lower rate, do you tend to get like substantial discontinuities in your control input? Do you get like sort of stuttering?
so that can happen. And generally that's undesirable, as you kind of may have guessed or alluded to. There's lots of ways to get around that. So like a very common thing to do in that context, if you care, is to basically regularize. So with these kind of online applications, you're always warm starting, right? So you'll solve it, and then like 10 milliseconds later, you're basically going to warm start it off the last solution. You're going to kind of time shift it 10 milliseconds and solve again, right, with a warm start. So if doing that warm starting, it tends to not go too far away. But you're absolutely right. If you get knocked really hard, it might go really far away. And if that's undesirable for various reasons, an easy thing to do is regularize it. And what I mean by that is when you do this time shifted thing, you have the last solution, right? So you can basically put a quadratic cost in the new problem that says, don't go too far away from the last solution that I warm started you with, right? That's called regularization. It's also called Damps-Newton. But yeah, basically you can play games to make that not happen if you don't want that by like shaping the cost function appropriately, which is a common move. Yeah. Yeah. Let's see what else. Okay, so then speed-wise, DDP is sort of commonly known for being really fast, which it is. It's also easy to implement fast DDP solvers. Like all the math is there, and like if you just code this up reasonably well, it's going to be fast. So it's sort of fast out of the box without you having to work too hard. Yeah, I mean, as long as you implement it well, like DDP tends to be very fast, and actually the rollouts can be a feature or a bug. From a speed perspective, like by doing that rollout, you're making sure that whatever's there obeys the physics and is dynamically feasible, as in you can go run that on the robot right now, even if it hasn't fully converged, right? So that can be helpful. It's basically easy to write a fast one. Whereas dircol, if you use an off-the-shelf solver like IPOpt, typically those are not as fast. You can make them go fast, but it's quite a lot of work. Like writing your own SQP solver from scratch for online MPC is hard. It takes a lot of work. It's possible, but basically it's much, much harder. And out of the box, DDP is almost certainly going to be faster than like IPOpt or something like that.
You fill out the sparsity information that IPOpt wants, will that like be as fast as DDP or like comparable, or what's still like?
It's still probably going to be slower. You should do that. That helps a lot. But it's probably, IPOpt with all the right sparsity stuff is still generally going to be slower than DDP. It's all problem dependent, obviously, but the reason is that like IPOpt's really designed to be an offline thing. I mean, people use it for online stuff, right, for sure, and you can make it work, but it's designed to be, it's basically designed for robustness rather than speed. It's designed to like try to get you a solution to a hard problem that you hand it. And it has a lot of safeguarding and checking and stuff like that, that is, again, all for robustness rather than speed. Whereas DDP, usually there's like very few guardrails in there, and it's just you just let it rip. And you can tune that offline and Monte Carlo it so you're pretty sure it's going to work. And then like basically get rid of all the guardrails for the online version so it's as fast as possible. Like that's kind of what you would do. Yeah. So fun fact, right? We saw how like the LQRQP, right, Riccati is basically a sparse solution to that. So that actually carries over. You can write an SQP method that uses Riccati as the sort of internal matrix factorization solve, which people do for speed. So they're not that, they're close connections here all over the place, but generally speaking, it's easier to make DDP go fast than it is to make dircol go fast. Let's see. Yeah, so like similarly, right, it's pretty hard to write a large scale like a large scale QP solver. That's a hard thing. Large scale SQP. Whereas it's actually pretty easy to implement your own DDP. Like you guys have done it, right? And that's pretty easy to implement on embedded systems. So if I have like a Raspberry Pi or something on a robot or a microcontroller, like, and I need to make this work, I'd probably implement DDP. It's, again, straightforward. It's pretty lightweight, blah, blah, blah. And then kind of the last one I'll mention is that you may have already seen hints of this, but like generally speaking, these large scale SQP solvers, they're super robust. They have lots of guardrails in them, and they tend to be numerically very robust. Like they've got lots of features in there for dealing with ill-conditioned problems and infeasible constraints and all that stuff. So they tend to be pretty bulletproof. Whereas if you write your own DDP, you know, it's not. And you might have to like do a lot of tuning and stuff to make sure it doesn't blow up on you. In particular, these kind of DDPs can have issues with ill conditioning, especially if you are trying to like handle constraints, like state constraints via penalties or something like that. That can get nasty pretty quickly. So if you've got lots of state constraints that you really care about, you're probably better off doing like an SQP thing, or at least it'll be more straightforward to implement. Okay, so that's sort of the high level pro con story there. Yeah, I would say high level DDP is often considered like a good choice for online real-time applications where you care mostly about speed. Whereas DIRCAL is like often the method of choice for like offline stuff where you care about getting the answer. You don't care if it takes 30 seconds. You're willing to sit there and you maybe have like complicated constraints and stuff like that. High level. Cool. Any questions about any of that? Okay, awesome. Now it is time to switch gears a bit. So here begins our journey into the fun world of attitude. So just quick, who's done like SO3, you know, SE3, little group theory stuff here and there? Not too many. We got like 3 hands. Okay, so this is gonna be down the rabbit hole time for everybody then. Good times. Okay, so high level story. First, I'm gonna tell you why you should care about this. And if you haven't seen this before, you know, maybe this is a shocker, but basically, many robotic systems, basically anything that has a floating base, right? So, you know, let's see, many robotic systems undergo large rotations. So let's see, some examples would be obviously quadrotors, airplanes, spacecraft, all the aerospace-y things. Whereas where a lot of these ideas originally come from, underwater vehicles. What else? Legged robots. If you go do parkour, if you do backflips, you've got this situation. Yeah, so lots of cool things, right? Anything like, you know, aggressive, you know, floating base, like this comes up, right? And the story here is like naive angle parameterizations that you've probably all seen before. So the biggest culprit here being Euler angles. It's like, who's used Euler angles in here? I would expect that to be like everybody. Yeah. So I'm here to tell you that Euler angles are bad for you and you should never use them, ever. Like there's never a reason. They're the worst. They're garbage. Get rid of that. I don't want to see that in here. So these things have all kinds of problems. Like they have singularities where your Jacobians kind of go singular and that blows things up. They're numerically terrible. Yeah, they're just bad. There are lots of mess of trig functions all over the place. There's nothing good about these. So numerical singularities that cause failures and or require lots of hacks to work around that are just gross. And we don't want that. I don't want that for you. Okay. So yeah, here we go. So there's lots of other approaches. There's a million ways to do this. And in here, we're going to sort of double down on 2 representations that are kind of the ones that are good, basically, which are rotation matrices, which everybody hopefully has seen before. And then the other ones that are slightly weirder, but also very common in applications are quaternions. Who's played with quaternions here? We get a quick show of hands. Most of you have seen these before. Okay, great. Who feels like they understand quaternions? That's the bigger question, right? Like nobody understands these things, right? So hopefully we'll try to address some of that. So these guys, these are nice because they're singularity free, right? And that means like they have no places where Jacobians blow up. They don't do weird crap at 90 degrees. Like they don't do anything that, you know, they behave themselves. But they have some other quirks, namely they're they're not a minimal coordinate representation, right? Rotations, we all know, pitch roll yaw, there's 3 degrees of freedom. But these things, Quaternions have 4 numbers, and rotation matrices have 9 numbers. So they're over parameterized. And what that really means is there's implicitly a bunch of constraints on these guys, on these representations, right? Because under the hood, there's only 3 degrees of freedom. So that means in the case of a rotation matrix, you're using 9 numbers to represent a 3 degree of freedom thing. So there's somewhere in there, there's 6 constraints actually on that rotation matrix. We'll talk about that. Quaternion, similarly, there's 4 numbers. There's 1 constraint to make that 3 degrees of freedom. So there's some subtlety then about, sort of how you optimize these things. So we're gonna do that. And sort of obviously from this constraint perspective, if I know what those constraints are, in principle, I can just bake those constraints into my optimization problem. But it turns out there's better ways to go. So we're going to talk about that. Okay, cool. So that's setting the stage, can calibrate a little bit. So the first thing to talk about is just what is attitude, which is a little bit subtle and not obvious. Can anyone give me a clean, self-contained definition of attitude? So I write it down as Euler angles or rotation matrices or whatever, but what actually is it physically? What does that matrix mean?
Orientation.
But what is that? How do I define orientation? Is basically what I'm asking. So the working definition that we'll use that's pretty standard in engineering, but it varies actually, is that it's the rotation from some body fixed coordinate frame on the robot to some global inertially fixed coordinate frame that you make up, so world frame. So it's typically we use it, and in here, so I'll just cartoon this out. So we've got some coordinate frame that is inertially fixed. So some we'll go with xn, yn, zn. We'll use these little left superscript n's to mean inertial frame. It's n for Newtonian frame. So there, and then we'll have some body frame that's maybe floating around out here that's fixed to our drone or whatever. And this is going to have its own coordinate axes. So we'll write B for body frame. So XB, YB, ZB. And the deal here is the rotation matrix or Quaternion or Euler angles, whatever that we write down that specifies the attitude of our system, of our drone or whatever. What it really is the rotation between this body frame and this world frame. We're going to write it here. We're going to introduce these little decorations just for bookkeeping for a little bit until you get the hang of it. So in here, we'll use left superscripts on the vectors. And then what you can do then is the rotation matrix, we're going to decorate it with superscripts on both sides. And this means that this guy is the rotation from the B frame to the N frame. And specifically, this is nice because I can write down. So if I have some random vector V in the N frame equals Q times V in the B frame. So if you kind of watch these superscripts, they kind of go left to right or right to left here, and you can kind of do the bookkeeping that way. And so if you have lots of different reference frames, these decorators are helpful because they let you kind of like chain rule through a bunch of coordinate transformations and line them up nicely. But that's the definition, right? So it's really the rotation from the body frame to the world frame. And so specifically what this is doing is rotating a vector defined in the body frame into the world frame. So the way to think about this is like if you've got like a camera bore sight vector and you want to know like what that thing's pointing at in the world, you take that bore sight vector, multiply it by Q, and now you know what that vector is in the world frame, right? Or if you've got a gyro that's strapped down on the body, right? That's telling you omega in the body frame. If you want to know what that rotation, omega is in the world frame, it's Q times omega, gives you the world frame version, right? Cool. Okay, so, and then the other thing, obviously, that we need to say is that this thing it's 3 degrees of freedom. But there is no, it turns out you can prove this pretty easily. There is no globally non-singular 3-parameter attitude representation. So in some deep sense, while this is a 3-dimensional object, you cannot write it down with 3 numbers globally, which is kind of a funky thing to think about. It's actually not that weird. We're going to talk through this and get you some geometric insight into this. If you're curious, this was proven in I think the early 60s by a guy named Stulpnagel in the aerospace literature. You can go look it up. So basically, you can never use 3 numbers globally. You can use 3 numbers locally for small angle rotations, but you should never use Euler angles. There's better 3-parameter representations for the local stuff too. All right. Questions about that? So far, so good. All right, nice. Okay, here we go. Yeah, we'll get there in a sec. What it means is that if you were to write down like the Jacobian mapping like Euler angles into anything else. So for example, if I were to convert the Euler angles to a rotation matrix and write that Jacobian down, that Jacobian will become singular. If I were to write down the forward kinematics of my robot, mapping, literally anything, that the Jacobian associated with mapping like Euler angles into something else becomes singular. That's like what it means. Basically, it means they blow up somewhere. And we'll clarify this as we go. We got to write some more math down to give you a tight definition. Okay, cool. So that's that. Okay, so first thing we're going to talk about then is rotation matrices. We're going to dig into rotation matrices a little bit and maybe show you a few things that, hopefully you've seen before, but maybe we're not clear. Okay, so rotation, another name for rotation matrix is direction cosine matrix. Anyone heard of that before? A few people? Yeah. And there's a kind of reason for that hopefully will become clear. Okay, so here's some interesting little like nuggets about rotation matrices. So I'm going to write down my give it just any world frame vector. Oops, 2, 3, I can't count. And then we're going to write down our rotation matrix here, and then some body frame vector. Cool. So now I'm going to ask you, can you tell me so this is just some vector. It's the same vector, but written in the body coordinate frame versus the world coordinate frame, right? And the rotation matrix is mapping these things into each other. So what I want you to think about right now is, what does matrix vector multiplication look like? You're basically taking the dot products of each row of that matrix with the vector on the right. So like x1n equals the first row of that rotation matrix dotted into that vector on the right, right? So thinking about that, I want you to tell me what the rows are. What are the row vectors of this rotation matrix? Think about like basis vectors of coordinate frames for a sec. So the first row of the rotation matrix dotted into xb gives me the first component of xn, right? So what does that mean? No. So if I think about the basis vectors of my coordinate frame, x1n is the component along the first basis vector of the n frame, right? So that basically means the first row of the rotation matrix is the n frame basis vector, the first n frame basis vector, right? Because it gives you the first component in the n frame, right? So this guy is the n1 basis vector, but in order for it to, multiply the body frame vector on the right, that means it's got to be expressed in B frame components, right? So little mental gymnastics there. Hopefully this is making sense to you, right? So this guy, N1 B, like this guy, N1 dotted into whatever's on the right, gives me the first component in the frame, right? That's what it's doing. So it's got to be the N basis vector written in B components, right? And similarly, all the rows are this. So this is N2 in the B frame. This is N3 in the B frame. Is everyone clear kind of on how that lines up? So they're just the basis vectors of they're essentially what this is really giving you is this mapping between frames by giving you the basis vectors of the output frame in the coordinates associated with the input frame. So it's like matching those things up. Does that make sense? Cool. I don't know. Chew on that a little bit. So now the question is, what are the so I should write down. This is right. This is our Q B to N or whatever. So now the question is, what are the columns? And you can get at this by just thinking again about the definition of matrix multiplication. So the columns here are doing the same stuff, but they're associated with, so each column, so the first column now is hitting the first element of the vector on the right, right? So this is x, b. So when I do this multiplication again, like this dot product thing's happening, right? But the first element here is hitting x1, and then next row, right? The first element here is hitting x1, right? So all the stuff that is hitting x1. So I don't know. Anyone want to take a guess?
It's the basic vectors in the other direction.
Yeah, exactly. So they're the B frame basis vectors written in the N frame components.
Yeah.
Yeah. So this is B1N, B2N, B3N, where they're the basis vectors the other way. Kind of cool. So basically this thing is, either way you look at it, it's the basis vectors of one frame expressed in the other coordinate frame. And you're just doing a bunch of dot products. Okay, so now that you know this, what does Q transpose Q equal? Yeah. Why? For the rest of us. Yeah, so right, exactly. So these are basis vectors, they're orthogonal. So literally what I do, if I do Q transpose Q, you can think of it either way. It's either the B frame or the N frame basis vectors dotted into themselves. So like N1 dotted into N1 is 1. N1 dotted into N2, N3 is 0. Same thing the other way. So the diagonals are the basis vectors dotted into themselves, and they're unit norm and they're orthogonal. So those are all 1s. But if I do any of the other pairs, right, it's got to be 0 because they're orthogonal. Awesome. So that tells you that. And this thing here, this Q transpose Q equals I thing, that is the definition of an orthogonal matrix. And like it all makes sense. Orthogonal matrix means the column vectors of the matrix are all mutually orthogonal. Makes sense, right? Okay, so that means orthogonal matrix. So other sort of corollary to this is, what is Q inverse? Yeah, exactly. So if Q transpose Q equals I, the definition of inverse is Q times Q inverse equals identity, right? So therefore, now we also know that Q inverse equals Q transpose, which is another way of defining orthogonal matrices, it turns out. Okay, so there's a bunch of weird special things going on with rotation matrices. So you have this internal structure where the columns are actually the basis vectors, and then you have this kind of fact that their inverse equals their transpose. Kind of interesting. There's one more special thing about these things that you got to know about. Maybe I'll move some stuff up here to write this down. So does anyone know what a determinant means geometrically? It's, yeah, area or volume. So basically what it ends up giving you is like, it's clear if you think about what it is in terms of eigenvalues, the product of the eigenvalues, right? So what that's really giving you is a volume. It's basically giving you, if you took the column vectors of this matrix, and here they make a box, right? It's the enclosed volume of the box, or the parallel pipette if they're not orthogonal, right? Whatever. If you basically take the convex hull of those basis vectors and get like a little parallelogram-y thing, it's the volume of that thing. That's what a determinant is. With one caveat, it's signed volume. Do you know what we mean by signed volume? You can have negative volume, and that's coming from right-hand rule. So if I take the first two columns, if the third column points in that direction, then it's positive volume. If the third vector points in the other direction, it's negative volume. So that's what we mean by signed volume. Okay, so based on that, and the fact that you know these are unit vectors that are orthogonal, what does the determinant of this thing have to be? Yeah, it's going to have determinant 1 because it doesn't do any. Another way of thinking about this is the determinant, it's this volume thing. It also defines how much if you think about it as an operator on vectors, it's how much it stretches the vectors, right? So if determinant is big, if it's positive, that generally means it's going to stretch vectors out. If it's smaller than 1, it's going to shrink stuff. And here it has to be 1 from this volume thing. Also, plus minus 1. Think about what if I have a regular right-hand rule orthogonal coordinate system, plus or minus 1. Yeah, exactly. Because of the sign volume thing. So if it's a standard coordinate frame that, with orthogonal basis vectors that obey the right-hand rule, it's going to have positive sign. It's going to have determinant plus 1. If I have determinant minus 1, that means it has a reflection in it. That's what that means. Does that make sense? The geometry. So we also have this thing where it has to have determinant Q equals 1. Okay, so those properties all together, the sort of Q transpose Q equals I and the determinant 1, that defines what's called the special orthogonal group, or SO3, in 3 dimensions. So the orthogonal part means Q transpose Q equals I, and the special part refers to the determinant equaling 1. What that's doing is it's eliminating reflections, right? So if you allow determinant Q to be plus or minus 1, that includes rotations and reflections. We want to get rid of the reflections, so we constrain it to be just determinant Q equals 1. Okay, so this is, if you put it all together, yeah, they have to be. Yeah. Well, so no, caveat. They have modulus 1. They're complex in general, right? So but they have to have complex modulus 1. But they can come in complex pairs that when you take the products, they have to be 1, right? Cool. Everyone good on that? So cool. This is good stuff. So this thing is what we call special. And if you put the special together with the orthogonal, you get, we write this the following way, which hopefully you've seen before. This is Q is in SO3, where the S means special, the O means orthogonal, and the 3 means 3D. If you say this out loud, you say Q is in SO3, or you say this is the special orthogonal group in 3D. And everything stays the same, except for if you want to make it, 4D rotations, it's SO4. The special and the orthogonal stay the same. You just have 4x4 matrices instead. So you can do this in any dimension you want. So the rotation matrices in any dimension have these properties. Cool. Okay. Any questions about that? So we're getting into some group theory now, but it's really just like all of group theory is really just matrix math. Like groups are just matrices. They're just classes of matrices with special properties. Okay. So not too scary. All right. So everyone good on that stuff? All right. So next up is we're going to talk about rotation. So this is basically, I would say, this is like how we think about rotations. Rotation matrices are the easiest ones, I think, to work with from this perspective. So next up is how do we think about rotation kinematics? And what that really refers to is how do I integrate velocities into rotation? So if I have an omega, so in other words, if I have a gyro, if I give you Q naught, so if I give you the initial conditions, Q naught, and I give you a perfect gyro on your thing that's wiggling around, how do I integrate omega to get Q of t? So if I give you Q naught and I give you omega of t and it's perfect, how do I take that time history of omegas and the initial Q and give you Q of t for all time? Does anyone know how to do that? So that's what we're going to do now. That's rotation kinematics. So we'll say that's how do I integrate a gyro. That's terrible. Okay, so we're going to draw some pictures now and do some thought experiments. So what we're going to do first is imagine I have like I don't know, like a record player. So we're going to have some like set of local coordinates, like so, let's say. And let's say this is like, some X and some body frame. This is some omega, and I've got maybe this like kind of disk over here, this record that's spinning around at some fixed omega, right? So if I were to take a point on the record, let me fix this. So this is just any X, right? What happened to my pen thing? That's weird. Oh, there's pencil mode and pen mode. I don't want pencil mode. Okay, so we got some circle thing here. And let's say, spinning at some constant omega, and this is just some vector xb defined. It's like you took a marker and painted a vector on the record, and it's spinning around, right, with some fixed omega. So that's the scenario. And now we can write down the vector x in the n frame equals, in this case, it's going to be q of t, because it's spinning around, so that rotation is changing, times some x, this body frame x, right? So that's cool. That's just definitions. So xb, the body frame one, I took a marker and drew this on the record. So in the record frame, it's fixed. But in the world frame, it's spinning around, so it's changing, right? So q of t is changing, but xb is changing. Is not changing. So now what I want to get to is, like, we're going to figure out, just from, like, I don't know, previous physics classes, whatever. Can anyone tell me what xn has to be? So anyway, like, this is called sometimes kinematic transport theorem or whatever, little cross product action. You remember this? So x dot, maybe you haven't seen this before. So if I have this thing spinning around and I have this omega up here, I take omega cross x, and that's going to give me the velocity of that thing as it spins around. Like, the tip of that x vector is given by omega cross, right? So hopefully you've seen that's like freshman physics stuff. So I can write down then in the n frame, x dot in the n frame is equal to omega in the n frame cross x in the n frame. So if I put everything in the n frame, at any given point in time, the velocity of the tip of that vector in the n frame is given by omega cross x. So, like, you can hopefully convince yourself that that's true. Usually this is derived in, like, some freshman physics class. Sometimes this is called the kinematic transport theorem or something like that. But yeah, it's just omega cross x. You can, I don't know, figure it out. It's not too hard. Okay, so now what we're going to do, so that's, like, hopefully intuitive from some physics. Now we're going to do this algebraically and just kind of chain rule this thing. So if I basically, I guess this is the product rule. I'm just going to diff it. So if I take this guy, that we sort of wrote before. So I have q of t times x in the b frame. So if I just diff this with respect to time, so I've got x dot in the n frame. I have q dot times x b plus q times x b. Man, that's terrible. Dot, just from, like, basic calculus stuff, right? Okay, so what can you tell me about xb dot? 0, because it's painted on the record. So in the body frame, that's 0. Cool. So this term is 0. So now we have the fact that xn dot equals q dot times xb. That's interesting. So, like, I'm going to now take that. Oh, yeah. Oh, we needed one more thing that I forgot to write down up here. So this thing, I wrote this all in the n frame, right? Up here, this omega cross x is in the n frame. I can rotate the whole thing in the body frame like this. That makes sense, everybody? Okay, cool. So now I have two versions of the same thing. I have x dot and xn dot written that way from right-hand rule stuff or whatever cross product stuff. I have it written this way algebraically. So now what I'm going to do is just set these equal to each other. And I'll get q dot times xb equals q times omega b cross xb, right? So this is this guy plugged in here. Okay, so now the question is, what is q dot? So basically all I'm asking for, right, is, like, I've got xb here. So basically somehow this q times omega cross thing has to equal q dot. That makes sense? I'm just, like, regrouping terms. So basically what I'm going to do is I'm going to pull the xb out of the expression on the right to the right and, like, group the rest of it. So the key little extra thing we need here just to make this algebraically work out is we're going to define this thing called the hat map. That's what I call it. You might have seen it before. It's if I write omega cross x, that's linear in omega and x, right? So I can therefore write this as a matrix, and we're going to write it as the following matrix. It basically all I'm doing is if I pull the x out to the right and write omega cross x as a matrix vector product, you'll get this matrix that looks like the following. So this thing times x1, x2, x3. So, and then we're going to write this as omega hat times x. So this matrix is omega hat. We call it the hat map. And it's just the cross product written out. It's like omega cross, that operation written as a matrix, right? Fun fact, any linear operation you can write as a matrix. So omega cross is a linear operation, you can write as a matrix. Cool. So now that we've defined that thing, I can write q dot from above there as q times omega hat, right? So it's q times omega cross x. So that omega cross x thing is the matrix omega hat times x. So now this is telling me that q dot equals q times omega hat, right? Just from like putting those two things together.
And it's still omega b, right?
That's right, yeah. So I rotated the whole thing into B frame. So I matched the frames up and then I get q dot. Yeah, basically let me like maybe write this out slightly more explicitly. So I've got q dot times xb from up above equals now q times omega hat times xb. And for this to be true for any xb, we have that q dot equals q. To be very explicit about the frames now, b to n times omega in the B frame. So that's the result we want. And this is the magic equation that lets you integrate the gyro. So now I have an ODE for Q of t, given Q naught, initial conditions, and given omega of t, time history of omegas. Now I have an equation that I can plug into RK4 or whatever and integrate up to get Q of t. Make sense? Everyone, yeah.
Can you just turn that into omega hat?
Yeah, you totally can. What would you do?
I mean, like you just, it is q and b times omega hat b just omega hat n?
No. Well, I mean, so literally you just hit it with another rotation matrix and rotate it back. It turns out what happens here is if you transpose the entire thing, it ends up being q dot for the n to b rotation equals omega hat in the n frame times q and b. Basically flip sides.
Yeah,
It's because the rotation matrix going the other way is just the transpose, right? So it turns out if you transpose the whole equation, you'll end up with omega hat in the n frame on the left side in that q times omega hat thing. It becomes omega hat times q the other way. Make sense? Yeah. So it just flips out. But yeah, you literally just plug the rotation in, flip it around. It's easy. So as an exercise, you can figure that out. Okay, so now basically we have the recipe. And so you can integrate the gyro, but more generally, right, you can now do kind of whatever dynamics you want in terms of rotation matrices. And this just kind of shows up as an ODE. Why might I not want to do that? So that's a little subtle, but yeah, there are ways around that, which we can talk about. But also more broadly, like this is a 9-dimensional object, so there's a lot of redundancy, which is kind of annoying. So oh, incidentally, what are the 6 constraints that you need? Because the rotation matrix is 9-dimensional, 3 degrees of freedom. What are the 6 constraints? Yeah, that's basically it, actually. It's because what you end up with there effectively are Q. It's basically all of, yeah, you end up with all of those sort of like the first column sort of times itself has to equal 1, and then the first column times the other two have to equal 0. So you have those for all of them. It turns out that's basically all of it. Okay, cool. So that's true. This is annoying, though. We have extra constraints, blah, blah, blah. So it turns out Quaternions, which are also sort of singularity free, they're only 4 degrees of freedom, or 4 numbers. So they're a lot more compact and efficient. So it turns out they are preferred. Yeah. That's correct. Yeah, 100%. Yeah, I mean, Q dot can be 0, right? If I'm not moving, Q dot 0. So, okay, Quaternions are more sort of compact and efficient for doing dynamics calculations with. So they are preferred in basically any application where you're doing dynamics. Quaternions are like the go-to. So they're pervasive in robotics, aerospace, computer graphics, even they're widely used. So they're a thing, and they're kind of the go-to choice if you're doing lots of dynamics. If you're just doing like coordinate transformations of vectors, rotation matrices are actually fine and just as efficient. Turns out the number of flops for rotating a vector between two frames is actually lower with a rotation matrix. They're close, but if you're doing dynamics, hands down, the Quaternion is the better choice. Okay, so what are we doing? Okay, so now we're going to talk about Quaternions. So here we go. Basically, and we're going to do this a couple different ways. And today will not be the end of our Quaternion conversation. So I'm going to give you like a little bit of like crash course today, and then we're going to circle back next time and do some more intuitive geometric stuff to try to like derive these things for you in a way that's hopefully going to give you some insight. Okay, so here's what we're going to do. First, we're going to define an axis of rotation, which is a unit vector. And we're going to call this thing A for axis. And then we're going to define an angle of the rotation, which is a scalar. And we'll use radians because we're reasonable people. And we'll call that thing theta. Cool? So now we have A, it's a unit vector. We have theta, it's an angle. We're given those two things, we're going to now define this thing that we're going to call phi, which is A times theta. So this is a 3D vector whose direction is the axis of rotation and whose magnitude is the angle of rotation in radians. Has anyone seen this before? Cool. Yeah. So these show up a lot. And there's deep reasons, deep fancy math reasons why they show up a lot. We don't need the deep fancy math reasons quite yet, but I'll give you some hints later. So this thing, we call this an axis angle. And this guy is, vector in R3. And it has the property that the norm of phi equals theta and phi over norm phi. So if I normalize the vector, that's A. Cool. So we can go back and forth between these two things. And sort of the important thing here, which is now getting a little deeper, is that if I have a constant omega for a short time, so like short time integration of my gyro, right? Short time step h, let's say. You can think of this phi as the integral of omega. So, I mean, this is true for short time scales and for like small angles or whatever. This is true. So over a little time step, if I just integrate omega of t dt, that's basically what this thing is, right? And in fact, this is one of the ways you integrate a gyro in practice. This, though, is not true in general. As in, for longer time scales, this is wrong. But over short integration time, like if you're doing this at 100 hertz on your system, like this is actually what you do in practice. You basically take your omega, multiply it by a dt of 10 milliseconds, and then, calculate this thing. Okay, cool. So now that we know this axis angle thing, we can easily define the Quaternion in terms of this guy. So in terms of axis angle phi, you can define a Quaternion. And okay, so Q, our Quaternion, remember, it's 4-dimensional. And traditionally, people talk about scalar and vector parts of Quaternions. And there's a bunch of ways to write these down, so be very careful. But I'm going to write it the following way. So this is cos theta over 2, which is a scalar. And then the bottom is A times sine theta over 2. Right? So the bottom part, the top part here is a scalar, and we're going to call that scalar part. And the bottom here is a 3D vector, and we're going to call that the vector part. Okay, first question. What is the length or norm of this four-dimensional quaternion. Why? Because what? Yeah, but why is this 4D thing with a sine and a cosine in it have to be unit norm? Yeah, because sine squared plus cos squared equals 1. That's why. All right, so here, right, so I've got Q transpose Q equals 1 because Q transpose Q is going to give me cos squared plus sine squared, right? So what this is telling you is that valid rotations, so quaternions, I can write down a quaternion that's not unit norm, right? But that quaternion will not be a rotation. In general, it'll be a rotation plus a stretch, right? But just rotations, valid rotations, correspond to unit quaternions. And a fun fact here, right, is that rotation matrices, if I do like numerical integration and I get drift where it's not quite SO3, not quite orthogonal, whatever, those are a pain to like normalize back to a rotation matrix. You can do it. Anyone know how you do it? Fun fact. How many guesses? Turns out you have to SVD it. So if you SVD it, you get a rotation matrix times a diagonal matrix times a rotation matrix. You take the SVD and then you basically like set all the singular values to 1 and smush it back together. So that's how you do it for a rotation matrix, which is a pain. For a quaternion, you just have to normalize it, like just, yeah, which is super easy. So much, much easier to normalize.
So it's weird that if I just scale multiply Q by say some constant K, it's not a rotation anymore.
So if you think about it as a linear transformation, it's a rotation plus a stretch. If it's a transformation on a vector, right? You could do the exact same thing to a rotation matrix and it would do the same thing, right?
I think it's like the system would stay the same.
Yes.
We rotate around the same.
Exactly. But it's now going to stretch the vector. Yeah. Cool. Okay. So next question, staring at this thing. Can anyone see what happens if I were to negate Q? Like think about Q versus minus Q. Yeah, why?
Because you're rotating the negative amount about the opposite.
Yeah, exactly. So that's a good way to see it. That's the geometry. You're flipping the rotation axis and then rotating the opposite way. So it's the same. That's very good. You can also see it algebraically because if I like do minus Q on there, cos is even function and sine's an odd function. You can kind of see it that way too. But yeah, perfect. You nailed it. So other fun facts here, we got Q and minus Q correspond to the same rotation. Has anyone heard of this before? I know some of you have. So anyone know what a name for this thing is? Anyone heard of this? It's called a double cover. Yeah. So that's a bit of a quirk. You can see this also if you just add 2 pi to theta here. This is called a double cover. And you have to sometimes be a little careful. So quaternions, unit quaternions, they'll say the full thing is they double cover SO3. That means there's 2 quaternions for every rotation matrix. Let's see. So yeah, and then the next thing to say here, which will now just kind of run down a whole bunch of them, is that really in most cases, you can think of a quaternion like as a rotation matrix, and there's a bunch of equivalent operations, and they basically work the same way. So operations on quaternions are all analogous to rotation matrices. So said another way, they basically act algebraically essentially the same way. And that's usually a pretty good way to think about them. So now we're just going to run through a whole bunch of those. So the first one is quaternion multiplication, which is the same kind of equivalent deal as if you were to, so if you wanted to chain rotations together, right, you multiply rotation matrices kind of right to left, same thing here. So to define this, we got, so quaternion Q1 times quaternion Q2. I'm going to use this little asterisk thing to write that down. Often people write it as the O times circle with the cross. We don't want to do that because we also want to use Kronecker products. So I use like the star, whatever. So if I write this in terms of the scalar and vector product parts, I'm just going to write these things out real quick for you guys. We'll go a little deeper into the geometry and the intuition next time, where you can derive these things, but right now I'm just going to give them to you. So it turns out this is interesting also historically because the quaternion product contains both the vector dot product and cross product in it, and actually historically came first, interestingly. So quaternions were invented by Hamilton, actually before kind of modern conventional vector notation was invented. Modern vector, like vector dot and cross products, were invented by Gibbs like 20 years after Hamilton invented this stuff. And it was done because everyone hated quaternions and didn't understand them. And Gibbs like simplified it down to like the dot and cross product operations in 3D to try to like make it a little friendlier for people. But it turns out these were older, and like Maxwell's equations were written down before Gibbs invented modern dot and cross product stuff. So originally Maxwell's equations were actually written in terms of quaternions, which like is kind of a weird historical accident, I guess. Okay, so that's what it is. It's got like scalar times scalar minus the dot product of the vector parts, scalar times vector, and then one cross V2. So it's kind of got both things floating around inside it. And unsurprisingly, this is a linear operation, and we're going to write some matrices down just that are helpful for us when we end up doing optimization, because we got to diff through these a lot of times. So if I want to take the derivative of like this thing with respect to Q2 or Q1, right? How do I do that? And so you do that by basically we're going to use the hat map trick again, but on this guy. So I'm going to define two matrices that I'll just write down. Then I'm going to call L and R, which are the right product and left product. And the way to think about it is I take that Q1 times Q2 thing, and I'm going to factor out for this one. I'll write it down real quick. This is basically if I pull Q2 out to the right of that expression, and like all the stuff associated with Q1, I pack into a matrix, right? It's that. Is that clear to everybody? So that matrix times Q2 gives me Q1 times Q2. I can do the same thing where I pull out the Q1 stuff to the right. And that is going to look like the following. Okay, so this we're going to call L of Q1, and then this one we're going to call R of Q2. And so what this is basically just saying is I can write that quaternion product as L of Q1 times Q2 or R of Q2 times Q1. It's the same thing. Not that useful yet, but it's useful when I need to diff this, so I can like chain rule through it. Okay, so that's that stuff. What else we got? Okay, another useful thing is, so when I want the opposite rotation, with a rotation matrix, I take its transpose, right? Equivalent to the inverse. So the quaternion equivalent to this is called the quaternion conjugate. And basically, it's really easy to figure out if we go look at the definition up here. I want the opposite rotation. So literally all I do is I keep the axis the same, and I flip the sign on theta. So what does that do to that guy? Does it do anything to cos? Right, cos is even. So cos minus theta is the same as cos theta. So the top part stays the same. What about sine of minus theta? Flip sign on the outside. So literally what I do is I flip the sign on the vector part of the quaternion and leave the scalar part alone. And then the notationally, this gets written with a dagger, superscript dagger. In LaTeX, it's slash dagger, right? That's just, it looks very much like a transpose, right? Like on purpose. And this is S minus V. And then going back to our matrix stuff here, where we got these LNRs, we're going to define a matrix version of this too, for convenience, for when we go do calculus stuff. We're going to write this as capital T times Q, which is just a matrix that's going to flip the vector part. So it's like almost an identity, right? And that's, again, so that we can chain rule through stuff and take derivatives. Cool. What else do we need to know? We've got how to rotate a vector by a quaternion. This one is not so hard to derive, but I think for now I'm just gonna show it to you, and then we'll do the derivation like next time maybe. So with a rotation matrix, it's literally just Q times X, right? Here it's a little different, but it's actually not that different if you think a little bit. So here's the recipe. So if I have a vector x that I want to rotate, I put it in as the vector part of a quaternion, and then I do this. Cool. So what does that look like for rotation stuff? That looks like how I rotate a matrix, right? When I do coordinate transformation on a matrix, I rotate the input and the output, right? And I sandwich it on both sides. So what this is really doing is it's analogous to how I would rotate a matrix as opposed to rotate a vector, right? So kind of interesting. There's more to that. And if I go write this out in terms of my L's and R's and T's and stuff like that, I can, back to the matrix thing, we're going to also define a matrix version of this for convenience. We're going to call this H for hat times X, which should be sort of, so this H is literally just 0i. So it's taking a 3 vector and like promoting it to a 4 vector with a 0 on top. And it turns out, hint, hint, H for hat, pure vector quaternions, where you just have a vector part and 0 scalar part, algebraically act exactly the same as the hat map for rotation matrices. And the reason is, if I go back up here and look at the product rule, if I have pure vector, the bottom part is literally just a cross product, right? So these things act like cross products, and they act like the hat. Right? So this promotion with this H to a 0 scalar part, pure vector part, is algebraically acting like the hat map for rotation in rotation matrix land. Cool. So that's good to know. What else? Okay, so knowing that, I can write this stuff in terms of our L's and R's and stuff as H transpose L of Q, R transpose of Q, H, X, B. I can also write it as H transpose R transpose of Q, L of Q, H, X, B. Those are equivalent. That's just me taking this stuff and like grouping it one way or the other, right? So if I do the left term, so if I do Q times that X there, that's L of Q times H times XB, right? And then I can do the other side is a right multiplied by blah, blah, blah. So this makes sense. So I'm just grouping these and writing them in our matrix stuff. And the important thing is these expressions are equivalent. It's just a question of order of operations on which terms I do first. And what is that thing? That's the rotation matrix Q, right? So this is how you convert a quaternion to a rotation matrix. This is big Q as a function of little q, and either one of those is equivalent. They give you the same answer. Okay, so now you know how to convert rotation. Now you know how to rotate a vector, and you know how to convert quaternion to rotation matrix. The last one I'm just going to throw at you because we're almost out of time is Quaternion kinematics. So it shouldn't be surprising, and if I sort of force the issue, you could probably figure this out at this point, but it's super analogous to the rotation matrix case, right? So remember, rotation matrix, it's Q dot equals Q times omega hat. So knowing what I told you about the hat map and this little H thing here, you can probably figure it out. So it's for quaternions, it's Q dot equals, it's almost Q times H times omega, but there's a 1/2 in here, which we'll talk about in a sec. Oops, sorry. It's 1/2 Q times this guy, which I said is analogous to the hat thing, which is, if I write this out, then it's 1/2, it's L of Q for left multiplied by Q times H times omega. And this L of Q times H thing, right, is a 4/3 matrix. It maps the 3D omega into the 4D quaternion. The 1/2 there, by the way, this is easy to derive. We'll do it next time. The 1/2 is coming from the theta over 2 stuff in there, right? Which is coming from the double cover. So all the factors of 2 floating around in here are actually coming from the fact that it's a double cover. They show up there, and they show up, if I diff that, they show up here on the outside. They also show up in the fact that quaternions are 4 pi periodic instead of 2 pi periodic, which is weird. Like if I add pi over 2 to theta, I get minus q. If I add another pi over 2, 2 pi, I get back to the original, right? So it's there's some weird stuff in there having to do with the double cover. There's factors of 2 all over the place because of the double cover. Okay, but yeah, basically now you have all, at least algebraic, you might not understand it super well yet, but like you have all the pieces to do any kind of simulation you want in terms of either rotation matrices or quaternions now. And maybe I'll leave you with one little thing. Just to make your point, which I think you made earlier, there's this little quirk of, so we said, okay, yeah, obviously there's a lot of redundancy in this thing, but there's also this quirk that if you have numerical drift in your integrator, things will not stay unit norm. So here's just all the stuff we just did, and I'll give you this notebook so you have code for these things. Hat map, L matrix, R matrix, T and H. These are all like the little things we just wrote down. This G is just L times A. It shows up a lot and it's convenient. And then here's Q of Q that we just derived. So what I'm gonna do now is simulate a rigid body tumbling. So I'm just making up an inertia matrix, 10 Hertz time steps, random initial conditions. Here's the continuous dynamics. So this is what we just derived, right? It's Q dot equals Q times omega hat. And then omega dot, this is Euler's equation for rigid body. I'm just stacking the rotation matrix up into my X state vector. So it's vec of Q, which we talked about, right? What that means. Stack the columns. Take RK4, all good. I'm going to simulate this for like, I don't know, what's that, 10,000 time steps or something, a bunch of time steps. And now we're going to grab the last Q out of this at the end of the simulation and look what happens if I do Q transpose Q. It's supposed to be the identity, right? It's pretty off though. It's actually not too terrible, but like it's off at like the 1e minus 6 level. And if you run, the longer you run the simulation, the worse that gets, right? I'm now going to do it with a quaternion. So here you go. And the key thing in here, remember, this is easy to normalize. So the trick is you use RK4 and just renormalize the quaternion at the end of your RK4 step every time you do it. And now I do this. This thing is perfectly unit norm at the end. And if I convert it back to a rotation matrix, which we know how to do, it's perfectly out to machine precision, like orthogonal, right? So that's why we use quaternions for simulation. It's faster and cheaper. It's easy to normalize at every step. And it guarantees that you kind of stay on the rails over long time simulations or whatever. Okay, we're done. Thanks, guys. Catch you next time.